Hello chemistry students. In this video, you will learn temperature conversion between Fahrenheit, Celsius, and Kelvin scale. You will learn how to rearrange equations. Then you will learn what is density, and we will do some problems related to density. And the last topic will be quantifying energy. Our first topic is temperature conversion. Most people are familiar with just one temperature unit, and it depends on which part of the world they live in. But there are three commonly used temperature units, and these are degree Celsius, degree Fahrenheit, and Kelvin. In United States, we are more familiar with Fahrenheit scale, and for us, 30 degree is cold and 100 degrees is hot. But for the rest of the world, nobody uses this scale. They use Celsius, and to them, 30 is pretty hot temperature. And scientific community typically uses Kelvin when doing calculations, and this is also SI unit for temperature, and to them, 30 is a very, very cold temperature. So why do we need to convert between temperature units? Well, there are different uses. We can convert between Fahrenheit and Celsius to see if it is hot in California or in Japan in a given day. We might also need to convert temperature from one of these scales to Kelvin in order to do some scientific calculations. Now let's look at the equations that can help us do the temperature conversion. But before we do that, we must understand some reference values that each of these scales uses. All scales define freezing and boiling points of water. Celsius sets the freezing point of water at 0 degrees Celsius and the boiling point at 100 degrees Celsius. Splitting up the space between freezing and boiling point to 100 parts called degrees. Fahrenheit scale sets the freezing point of water at 32 and boiling point at 212, splitting up the space between freezing and boiling point 180 degrees. So to understand how to convert between Fahrenheit and Celsius, we must know that Fahrenheit climbs 180 degrees in the same space that Celsius climbs 100 degrees. This makes Celsius degrees almost twice or 9 by 5 the size of the Fahrenheit division. We also have to take account for this 32 degrees discrepancy, and this will give us this formula to convert Celsius temperature to Fahrenheit temperature. And we can rearrange this to convert Fahrenheit temperature to Celsius. Now for the Kelvin scale, we can see that the scale is divided the same way as the Celsius scale, 100 degrees between the freezing and boiling point and 100 degrees between freezing and boiling point, but the reference value for the freezing point is different. Therefore, to convert from Celsius to Fahrenheit, all you need to do is to add 273.15 to the Celsius temperature. And remember that we will treat all numbers in the formula as exact numbers. Let's do some practice and convert 23.0 degrees Celsius to Kelvin. Remember that Kelvin does not have any degree, and this degree sign is only on Celsius and Fahrenheit. Formula to convert degrees Celsius to Kelvin is K equals temperature in degrees Celsius plus 273.15. Temperature in Celsius is given, and this is what we need to convert to Kelvin. When we add these two numbers, we have 296.15 K in our answer. Remember that we will follow rules for sig fig when we are doing any calculation. So here we are doing addition, and the rule for addition is that you have to look at the number of decimal places in the measurements being added, and the smallest number of decimal place will be in the answer. So here we have 1 decimal place, and here we have 2 decimal places. So in answer, you are going to have 1 decimal place, which is up to this point. And the rule for rounding is if the last digit to be keep is followed by a 5 and no other non-zero number, then you will round up if this number is odd, right? So we have this as odd number, so we are going to round it up as 296.2, and this will be the answer when you convert 23.0 degrees Celsius to Kelvin. Let's do some more examples, and how about you pause this video, solve these problems at your own with the help of the formulas that we have in the previous slide, then play the video to check your answer. So the formula that we will follow is degree Celsius equals 5/9 degree Fahrenheit minus 32. Let's plug in Fahrenheit temperature here. You have to be careful about the brackets and the order of operation. Okay, so this is the answer that I have on my calculator, and now we will do our sig fig check. For sig fig, you know that this 5/9 is exact number and 32 is exact number. The only measurement that I have is 98.6, and the operation that we are doing here is subtraction, and the rule for addition subtraction is that you will be looking at the number of decimal places. Here we have 1 decimal place, and we are not going to look at the decimal place in the exact number, right? So I'm not doing anything here. So 1 decimal place, and then you have this 1 decimal place here, right? The next step that we are doing is we are doing multiplication, and the rule for multiplication is that you will be checking the sig fig in the measurement that you have. So the measurement that we have is this one, and it have 3 significant figures. So in your answer, you are going to show 3 significant figures. Right now it is 37. To make it 3 sig fig, we are going to add 0 here, and with this 37.0, this will be 3 significant figures. Let's do another example, and again for this example, pause the video, solve it at your own, and then play the video to check the answer. Again, pay attention to the order of operation and the brackets that we have. Okay, let's check the significant figures. 32 and 9/5 are our exact numbers, so we are not going to look at anything like decimal place or sig fig in these numbers. The only measurement we have is 38.0. We are doing multiplication. The rule for multiplication is you have to check the sig figs. Here we have 3 significant figures. When you multiply this, your answer should have 3 sig figs. So this is your 3 sig fig. And when you are doing addition, you will be looking at actually decimal place. So this is 1 decimal place under this bracket that we have, right? So in your answer, you are going to show 1 decimal place, and in our answer, we already have 1 decimal place, so we don't need to do anything here. and this will be the answer. Our next topic is rearranging equations. In this course, you will be using a lot of equations and many times you will have to rearrange them for certain variable. The fundamental rule when rearranging equation is simple. You are not allowed to change the meaning of the equation, but you can change its appearance. On this slide, I have algebraic rules that will help us change the appearance of the equation. When you are trying to move a variable to the opposite side of the equation, you must do the opposite operation on both sides of the equation. And while doing that, we can add the same quantity to the both side of the equation. We can subtract the same quantity from the both side of the equation. We can multiply with same quantity from both side of the equation, and we can divide with same quantity from both side of the equation. Here I have example x minus y equals z. I want to move this y on the other side of the equal, and the operation right now is subtraction, so I have to do the opposite of this if I want to move this y from here to the other side of the equal. Opposite of subtraction will be addition, so I'm adding y to both sides of the equation. When I'm doing it, this y minus y and plus y, the opposite operations will cancel out, and I will have the new equation, which is x equals z plus y. In this example, I want to move this y on the other side of the equation, but this y is being added here. So the opposite of this will be subtraction. I will subtract y from both sides of the equation. And again, this will be canceled out. And I will have x equals z minus y. In this example, x and y are being divided, and I want to move this y on the other side of the equal. So the opposite of this divide will be multiply. I am multiplying both sides of the equation by y. And when I do that, this y will cancel out, and I will have x equals z times y. In the last example, I have xy equals z. I want to move this y on the other side of the equal. Here it is being multiplied. If I want to move it on the other side, I have to divide by y both sides. So divided by y here and divided by y here. So this will cancel out like here. And after that, I will have x equals z over y. Our next topic is density. Density is a physical property of matter that expresses a relationship of mass and volume. This is a property that tells you how much mass is in a given volume. The more mass an object contains in a given space, the more dense it is. For example, a rock is more dense than a crumpled piece of paper of the same size. Or a styrofoam cup is less dense than a ceramic cup of the same size. On the screen, you are looking at the definition of density, which is density is defined as mass per unit volume. And its formula will be density equals mass over volume, or if we use symbols, then it will be D equals M over V. Unit of density comes from the formula, as the unit for volume is different for solids and liquids. Unit of density is also different for liquid and solid. For liquids, the unit of density is grams per milliliter, and for solids, it is grams per cubic centimeter. Each substance has a unique density associated with it. Density is an intensive quantity, which means it is independent of the size. As the sample increases, both mass and volume increases in the same ratio. So the density will always be same for a substance regardless of its size. In this table, I have densities of some common substances, and you can notice that the last three densities in the table, all gases, have much lower densities than the liquids and solids. Helium is even lighter than air, and that is why helium-filled balloons float in the air. If you look at the density of water, liquid, and solid ice, you will notice that ice is less dense compared to the liquid water. And that is why ice floats on the water. And in later chapter, you will see why water, being the same substance, have a different density in two different state of matter. Let's solve this word problem to determine the density of mercury. So the problem is mercury metal is poured into a graduated cylinder that holds exactly 22.5 milliliters. The mercury used to fill the cylinder weighs 300.0 gram. From this information, calculate the density of mercury. You have the formula to calculate the density. How about you pause the video and try to solve it at your own with the help of the formula, and then play the video to check the answer. To find density, we need mass and volume of mercury. Volume of mercury will be equal to the volume of the container it is poured in, which is 22.5 milliliter, and mass is 306.0 gram. With this information, let's find the density. Okay, we have 13.6 grams per milliliter. Like any other calculation, after having our answer, we will go back and check the sig figs. We are doing division, and the rule for division is you have to check the number of significant figures, and the lowest number of sig fig will be in the answer. So in this first, the top measurement, we have 4 sig figs, and here we have 3 sig figs. And your answer already have 3 sig figs, so you don't need to do anything further, and this is going to be the answer. And we are finding the density of mercury. Whenever the real data is given, the density of mercury will always come out 13.6, as you can see in this table. Let's do another example. In this example, we have a flask that weighs 121.3 gram when empty and 283.8 gram when filled with water, having a density of 1.000 gram per cm cube. And you have to find the volume of the flask. So let's start. This is a density problem. The formula for density is density equals mass over volume. But what do you have to find? You actually have to find volume, not the density. Density is already given. So it means that you have to do some equation rearrangement, or you have to move this volume from here to on this side of the equation or of the equal sign. In order to do that, right now this volume is in the division. We can do the same operation, the same opposite operation, multiply on both sides of the equal sign. So this will be cancelled from here. We also want to move this density from here. The density is right now being multiplied. If you want to get rid of this, you will be dividing it on both sides of the equation. This will be cancelled from here, and your formula will be volume equals mass over density. To find the volume, we need the mass of water. So the density of water is given. We need to know what is the mass of the water that is filled in this flask. The weights given are the weights of flask when it was empty and filled. If we subtract these two numbers, we will get the weight of the water. The way we are finding the weight of water is called weighing by subtraction technique. And you can watch a video on this technique, and the link for this video is given in the description box. Gram will be cancelled out, and you will have 161.9 cm cube as volume. There's a reason that I write all these units, and I'm even though I'm doing a subtraction, but I'm writing everything. And the reason, that for all these calculation, we have to make sure that the sig fig in our answer is right, and that can only be done if I have everything written like this, right? So the first step that I did is the subtraction, and for subtraction, we look at the number of decimal places. Here we have one decimal place, here we have one decimal place, and your answer also here, if you have to round, it will be up to this point, right? One decimal place. We are not we don't round in the middle. And the next thing is we are doing the division, and for division we check the number of sig fig. In this one, we have 4 sig figs. All these trailing zeros are significant. So we have 4 sig fig here, and under this bracket, we have 4 sig fig for this measurement. So your answer should have 4 sig fig, which we already have. So you're not going to do anything, but you will be showing all these decimal places and sig fig thing in your answer to show your understanding about the significant figures and how to handle them when doing calculation. So this is the answer for A. Now B is how much does the flask weigh when filled with carbon tetrachloride having the density of 1.59 grams per cm cube. Now again for this, so you have to find how much does the flask weigh. So your formula for density is density equals mass over volume. This time you have to find mass, right? So let's do the equation rearrangement. Do it exact same thing on the scratch paper, and you will get the answer, which is mass equals density times volume. So this will be the formula. The density of carbon tetrachloride is given. What about the volume? For volume, this volume that we just have find is the volume of the flask, right? And carbon tetrachloride is being filled in this flask. So this volume is actually the volume of the carbon tetrachloride as well, right? So we can use that volume to find the mass. Okay, so this unit is canceled. And the answer that I have is 257.421 is the mass of carbon tetrachloride. Now, this is the mass of carbon tetrachloride, but if you look at the wording, what do you have to find? How much does the flask weigh when filled with carbon tetrachloride? And this is just the mass of carbon tetrachloride. In order to find the mass of flask, you have to add this mass of empty flask to the mass of carbon tetrachloride. Okay, so this is the mass of the flask when it is filled with carbon tetrachloride. And remember that we are going to do our sig figs thing. So here we are multiplying these two numbers. We have 3 sig fig here and 4 sig figs in this. All right. If you have to round, we are not doing in the middle, but if you have to round, you will be rounding it up to 3 sig fig here, right? And the next thing that we are doing is adding these two numbers, and the rules for addition is you will be looking at the decimal place. So decimal place for this measurement is 1 decimal place, but the decimal place for this measurement under this bracket is 0 decimal place, right? So if you will be rounding this answer, you will be rounding it to 0 decimal place, which will be 379 because this is the last digit you need to keep, and the number after that is greater than 5. So this is going to be the answer. Our last topic is quantifying energy. Quantifying energy simply means giving units to energy. And a well-known unit of energy is calorie. We write this unit with lowercase c. The definition of calorie is that 1 calorie is defined as the amount of energy required to raise the temperature of 1 gram of water from 25 degrees Celsius to 26 degrees Celsius. And the SI unit of energy is joules, and there are 4.184 joules in calorie. Okay, so you need to remember this conversion factor, that whenever you have to do a conversion between joules and calorie, you will be using this conversion factor. This is also good to know that we have another unit of energy which is used by dietitians and food industry. It is also called calorie, but the difference is that this calorie is written by uppercase C, and this, just by making it uppercase C, it becomes like a kilo or 10 to the 3. So one uppercase calories are equal to 1,000 lowercase calories. The topic that we are looking at now is specific heat. The specific heat of a substance is the amount of heat energy required to warm 1 gram of that substance by 1 degree Celsius. This definition is very much similar to the definition of calorie. The difference is that it is not restricted for the water, like calorie is 1 gram of water, and also there's no restriction for the start temperature. In calorie, the temperature is from 25 to 26 degrees Celsius. But for specific heat, and it can start from any temperature, and the increase by 1 degree Celsius is the amount of heat that is called specific heat. For the unit of specific heat, it comes from the formula of heat, which is the specific heat of the substance multiplied by mass of the substance multiplied by change in temperature. And when we rearrange this equation for specific heat of the substance, we get heat divided by mass of the substance multiplied by change in temperature. The units that we have, you can see the unit of specific heat will come out joules per gram per degree Celsius, or if we are measuring heat in calorie, then it will come out as calorie per gram per degree Celsius. And also something good for you to remember is, like, the density of water is 1.000 grams per mil. Same is the specific heat of water is 1.000 calorie per gram per degree Celsius. So this is something that good to memorize. On this slide, you are looking at the specific heats of some common substances. So look at these values and then try to answer the question. Question is that suppose you have 1 gram of water and 1 gram of aluminum. Both are at 25 degrees Celsius and you want to warm them to 26 degrees Celsius. Would you need to add same amount of heat to each of them? You can pause the video and try to think the answer, and then play the video for the answer. The answer is that as the specific heat of water is much larger than the specific heat of aluminum, therefore it will take more heat to warm up a given mass of water than it does to warm up the same amount of aluminum. Once we know a substance specific heat, we can use that substance to measure the energy. On this slide, you are looking at a calorimeter, which is a device that is used to measure specific heat of a substance. The walls of the calorimeter are insulated, which means that heat cannot enter to this system and cannot escape from this system as well. The mass inside this calorimeter is 1.00 times 10 to the 4 gram, and that calorimeter is closed, means that there will be no change in the amount of the water during this reaction. The temperature of the water in the beginning is 25.0 degrees Celsius, and inside this calorimeter we have a bomb which actually have a Twinkie and enough oxygen to completely burn this Twinkie. When this Twinkie will burn, it will release heat. And heat, as the walls are insulated, cannot escape from the system, will all be absorbed by the water that is surrounded by this bomb. And when the water will absorb the heat, the temperature will increase from 25 to 45 degrees Celsius. With this information that we have here, we can see that there is a change in temperature, right? There is some amount of water that have absorbed the heat, right? And this water have its specific heat that we already know. Specific heat of water is 1.000 calorie per gram per degree Celsius. So with all this data, let's find how much heat is released by this Twinkie. The formula for that is heat equals specific heat times mass in grams times change in temperature. This delta sign is used to represent the word change, so change in temperature in degrees Celsius.